Go ahead.
Okay, so we're very happy to have here our next speaker, Leron Borsten from Edinburgh, and he's going to be telling us about color kinematics, duality, and double copy. So please go ahead. Thank you.
Okay, well, thank you for the invitation. It's really nice to be anywhere else in person, but especially Paris on a nice day. It's grim in Edinburgh at the minute. So I'm going to tell you about some work that I've done over the last year or so with my colleagues in the Czech Republic and Surrey and Edinburgh, Branislav Jurko, Bjorn Kim, Tommaso Macrelli, who's now actually in Switzerland at ETH, Christian Seymour and Martin Wolf. And the kind of big theme, the big picture is this relationship between gravity and gauge theory, which we've just had a wonderful account of. And this is obviously an idea that has reoccurred many times in the annals of theoretical physics, and perhaps the simplest, conceptually simplest incarnation, and one of the earliest is gravity as the gauge theory of one of the space-time symmetries. So you could consider the Lorentz group and consider just the Yang-Mills gauge theory over it. In 3 dimensions, this literally goes through. In higher dimensions, there are pieces missing, although it is a very powerful picture, say, for instance, constructing supergravity Lagrangians, even if it isn't the full picture. As we all know, there is a more recent and more powerful incarnation of this idea, the holographic principle. And I want to tell you about a third, and at least superficially completely independent point of view. So while the holographic principle relates gravity and gauge theories in different dimensions and is a full, strong, weak coupling duality, here I want to consider the notion of gravity as the product of 2 gauge theories, where everything lives in the same dimensions and everything is perturbative. Again, this itself has reoccurred many times in different guises. There's early work due to Feynman and Papini, where they took the notion of just tensor producting spin 1 representations to get spin 2 representations. But it really became kind of concrete and non-trivial with the advent of string theory in the guise of the KRT relations, which relate the tree-level closed string scattering amplitudes, the sums of products of open string amplitudes. But this really stopped at tree level, and there has been a semi-recent resurgence of this idea following some seminal work by Zvi Bern, John Joseph Carrasco, and Henrik Johansson that goes by the name of color kinematics duality and the double copy. And it tells us that there are some properties of Yang-Mills, some conjectured properties of Yang-Mills, that allow us to square the amplitudes or double copy the amplitudes to all orders in perturbation theory, given those properties hold. Those properties being color kinematics duality. So there are 2 obvious long-standing open questions regarding this picture. The first is, does color kinematics duality hold? Is it true? Or at least in some form that is sufficient to get the double copy to work, to get gravity from gauge theory? And that's the second question. Does the double copy hold? Is Einstein really the square of Yang-Mills to all orders in perturbation theory? Beyond perturbation theory, I have nothing to say. Other people do. I will briefly mention them. I just personally don't. Okay. And what I want to advocate today is that one approach to these questions that you could take is to try step away from the on-shell amplitude paradigm, which has been incredibly powerful and has uncovered this rich structure underlying Yang-Mills theory. But now that we have it, we could consider trying to go back off shell and considering the field theories themselves and ask the question, is color kinematics duality a property of the Yang-Mills field theory, not just its amplitudes? And what I want to convince you is that this is true, and in particular it's true of the Yang-Mills BV action, with an important caveat that this is up to counter terms. I'll explain as I go along more by what I mean by that. This is very natural. I will try to convince you that this is a very natural way of thinking about color kinematics duality, but I should emphasize it's non-conventional. It's non-conventional in the sense that these counter terms that I mentioned are required to ensure unitarity. and they actually break the color kinematics duality. But in this picture, this is seen as a regularization and renormalization effect. And in the unregularized, unrenormalized, just loop integrams, you have full color kinematics duality. For the aficionados of color kinematics duality in the double copy, those sentences should be worrying you. I'll explain why if it's not immediately obvious later. But those worries can be circumvented, and indeed you can use this to show that perturbative quantum Einstein-Hilbert gravity coupled to a Calderon-2 form and the dilaton really is the square of Yang-Mills theory to all orders of perturbation theory. Having described how all of this works, I want to end with some discussion of the mathematics of color kinematics duality. What it is, what are its mathematical principles? And there is actually a very natural, this natural notion of color kinematics duality leads us to the idea of what are called BV box infinity algebras. These are a very particular class of homotopy algebras. And the fact that it's a homotopy algebra, what that's kind of figuratively telling us is the fact that we don't see color kinematics duality in Yang-Mills automatically. You know, you write down the Yang-Mills action, color kinematics duality is nowhere to be seen there. You have to work very hard to make it manifest. This is really a statement that the fact that there is an underlying BV box infinity algebra is telling you that it really was there. It was just hidden up to homotopies. So there are homotopy relations that are telling you how to repair things to put in the color kinematics duality, to make it manifest. And this is also the fact that there is a homotopy algebra underpinning this color kinematics duality is related to the fact that to every Lagrangian BV theory, there is an associated L infinity algebra, another type of homotopy algebra. And in the case of Yang-Mills, it factorizes in a very neat way. It factorizes into a color part, which is just the bog standard Lie algebra of the gauge group, a kinematic part, which is kind of encoding the representation theory, the space-time representation theory of the theory, and the scalar part. And I've color-coded these, and I'll explain that color coding as we go along. So the scalar part, you can just think of as a scalar field theory with no dressing. And it's these two terms that turn the scalar field theory into Yang-Mills. Then the statement of the double copy is to say, I just take this color factor of this L infinity algebra and replace it by a second copy of the kinematics, and out pops n equals 0 supergravity. So I said, every Lagrangian BV theory comes with an L infinity algebra that is equivalent to it. It contains all the data of the theory. And I'm just telling you that the Yang-Mills L infinity algebra and the n equals 0 supergravity L infinity algebras are related by this trade.
N equals 0 supergravity, plus Calderon plus dilaton.
That's it. Yeah, it's what you'd expect from strings.
Sorry, just a very naive question. Is it understood what happens to higher derivative operators? If you correct Einstein-Hilbert by higher derivative operators, is this still supposed to?
That's a very good question. I think that there are instances where you can make this story work for some sub-discussion of higher derivative operators. Henrik Johansson has done work where they construct amplitudes of conformal supergravity by inserting high derivative operators in the Yang-Mills factors, but it's not clear that this actually holds to all points, even at tree level, let alone loops. So it's a good open question. So what are we going to discuss today? Well, I'm going to review color kinematics duality as it's normally presented. Then I'm going to revisit color kinematics duality in the way I'd like to present it today. After that, I'm going to introduce the notion of the Lagrangian double copy. I've actually called it, in the last paper, we called it syngamy, which is meant to evoke the meiotic reproduction of diploid chromosome sets, because that's how the double copy really works. You kind of tear the theories in half, and then you can put the two halves together in any way you want. And it's just a neat analogy. It really makes sense, so I put it there. So the point is, you can't, there's not just the double copy. You can do all sorts of things. So I could have replaced kinematics with color to get a biojoint scalar theory. That's kind of trivial. But I can take these half chromosomes and put them together of two different parent theories in any way I like and get out different offspring. So it's a bit, the double copy is really a bit more general than turning Yang-Mills into gravity. I'll say a little more about that later. And then finally, I want to discuss this homotopy algebra picture. And I don't expect to be able to say too much about that, but we can always talk about it afterwards, anyone who's interested. I've put there generalizations and supersymmetry. The kind of standard supersymmetric story actually goes through almost seamlessly. I won't say much about it, but again, if people are interested, I can kind of fill out the details. The goals are later. Okay, so the first part, just reviewing color kinematics duality. There's an initial trivial observation, almost trivial observation, that we can write an arbitrary endpoint L-loop gluon amplitude in terms of purely cubic diagrams. So, I mean, at 4 points, you've just got the S, T, and U channels, but you don't consider the 4-point contact term. And then the amplitude takes this kind of neat form, where we've got 3 pieces that I've color-coded to correspond to my color coding on the previous slides. I've got a color piece, which is just built from the structure constants of the gauge-Lie algebra. And these are just read off from the diagram. So the CIs are completely fixed just by the topology of each diagram. And the same is true for this propagator piece, the DIs that sit down there, D for denominator. They are also just read off from the topology of each diagram. And the bit where we've got some freedom is in these kinematic numerators, these NIs. They're built from the kinematic data, the gluon polarizations and momenta. They're just Lorentz invariant polynomials. And these are non-unique. I can adjust these whilst leaving the amplitude invariant. And that's what really allows you to put things into color kinematic dual form. I'll explain a little more about what I mean by that in a moment. So just to convince you that you can always do this strictification, making things strictly cubic, wherever you see a 4-point vertex in one of your Feynman diagrams, you can just replace it by a triple of S, T, and U channels just by inserting S over S, T over T, or U over U. So you pick up a Mandelstam variable in the numerator in the NI, but you kind of blow this 4-point contact term up into these 3 pieces. And that's all there is to it. I want to, for future reference, I just want to emphasize the almost trivial observation that you can realize this blowing up at the level of the Lagrangian by introducing an auxiliary field. So here I've replaced the usual 4-point contact term with something that's purely cubic and a kinetic term for this auxiliary field, the B field. And in this case, the Feynman diagrams generate these cubic amplitudes directly with just one subtlety, that when I'm talking about the CIs and the NIs, I really imagine that in the NIs, well, I don't imagine, I take the sum over all common topologies here. And what I mean by that is I just have to sum over all the different fields that can run on the internal line. So at 4 points, this NS, the S channel, is really composed of the S channel with the gluon 1 form sitting there, and then also the contribution from this auxiliary field sitting in the propagator. And this makes sense because the CIs and DIs are just determined by the topology, so you can always pull them out.
So is there an asymmetry that removes this additional field? It's not really an auxiliary field, right? It has a kinetic term. So.
Yes, so that's right. So at tree level, this operation is completely innocent. And actually, no, I mean, it's just completely innocent, full stop. I mean, if you look carefully at how, as long as you don't put the auxiliary fields on the external lines, they will never propagate anything, just by construction. Later, there is something more potentially insidious that we're going to have to worry about of that kind of nature. But yes, you want these to be genuinely auxiliary. But the way they've been introduced ensures that as long as you don't by hand put them in the external lines.
If you were having a content theory with normalization, you would be Maybe-
I will come to this point. In this case, no, this would be okay. Just because by construction, you can't ever produce them on the loops. There are no interactions that produce the B fields in the loops. So as long as you don't put them on the external lines, they will never appear. But later that will be a problem. I mean, if you're worried that this is just operationally completely equivalent to this operation, and now these diagrams could be sitting in arbitrary loop diagrams. So this is another way of just convincing yourself that this is completely innocent.
Well, this is more convincing to me, I guess, or as opposed to.
Yes, but these are what the bit where you have to convince yourself is just that if you take the Feynman diagrams that I just showed you, that this is operationally identical to doing this inserting ones everywhere. Yeah. Okay, so the color kinematics duality conjecture in that case is the statement that once you've put the diagrams in this purely cubic form, there is a reorganization. There always exists a reorganization such that whenever a triple of color factors satisfy a Jacobi identity, which they do all the time, right? They are the structure constants of a Lie algebra. Whenever the diagrams are diagrammatic representations of a Jacobi identity, this will hold. The non-trivial part is that whenever that happens, the kinematic numerators obey exactly the same identities. And this is completely non-obvious. I mean, there's no particular reason why you'd expect that to happen. And it suggests that there is some kinematic algebra underlying Yang-Mills. Okay, so this color kinematics duality is established at tree level. This was done very soon after it was proposed. And it's since been done from a variety of perspectives, from homotopy algebras to more stringy techniques. There is significant evidence for the conjecture up to 4 loops in various super Yang-Mills theories, but it very quickly becomes difficult to check, and it in fact remains conjectural. It just becomes computationally challenging.
Sorry, what is the same C goes from C and goes from?
This is just reflecting that the CI should be antisymmetric under the interchange of legs. So you can imagine your diagram just switching 2 legs, 2 of the indices on the Fs will turn around, and the same should happen for the NIs.
And 5 loop, it turned out to be more useful to avoid finding it and
yes, at 5 loops it got so difficult that it was better to generalize the notion of color kinematics duality and kind of half use it to use this generalized color kinematics duality and then bootstrap your way up to the answer. Yes, I will say a little about that in a moment. So now the double copy, given color kinematics duality, what is you can do this operation that you send the C's to the ends, and the claim is that this gives you a bona fide amplitude of n equals 0 supergravity. And that statement is not conjectural. There's a proof for that. So all the mystery here is contained in the color kinematics duality part. So this is conceptually compelling. It's suggestive of some kind of relationship between Yang-Mills and gravity, at least perturbatively. But it's also computationally very powerful. As Guillaume just mentioned, they've used this to compute supergravity, n equals 8 supergravity to 5 loops, and it turned out to be finite. This is a real tour de force of a calculation. This can actually, and if you had your 1985 supergravity hat on, this would be a surprising statement that it's finite, but it actually can be explained by supersymmetry. And you really have to go all the way to 7 loops before a finite amplitude would be surprising, would have no obvious explanation due to a known symmetry principle. And 7 loops is pretty daunting. But you can reduce the degree of supersymmetry, and then your protection against divergences fails earlier in the loop counting. And indeed, it's been shown that n equals 5 supergravity at 4 loops is finite, And there is no symmetry argument explaining this. And so the cancellations involved in this calculation have been dubbed enhanced calculations because they are calculations with no good explanation. I mean, it can't just be luck, but we don't know why it happens. And the intuition is that maybe there's something to do with color kinematics duality that's driving this. Disappointingly, these cancellations were not seen for n equals 8 of 5 loops. I mean, it's finite, but you can study whether it's finite because of some special properties or it's just finite because it should be finite. And I think ultimately the implications of these observations remain unclear. It's unclear whether these enhanced cancellations persist for higher orders, whether they're sufficient for finiteness. I mean, we need a better understanding of what's going on. A better understanding plus more calculations. So that was some background and motivation from the point of view of understanding divergences in supergravity. We can go all the way to the other end of the spectrum and consider classical solutions, and in particular applications to gravity wave astronomy. You can actually use the double copy to generate either non-perturbatively in very special cases or perturbatively solutions to Einstein's equations, just classical solutions. And in fact, this is turning into a very active and quite impressive field in its own right. There are also stringy considerations. There are geometric and worldsheet pictures of the double copy. As you might imagine, there should be some open equals closed picture underlying this, perhaps. And you can also turn it around. In fact, you can use the double copy to take amplitudes from field theories, square them together, double copy them to get out string amplitudes. That's another way of thinking about this. So given this kind of classical, this emergence of this classical double copy, it becomes more natural to ask whether there really is an off-shell realization of color kinematics duality in the double copy. And that's the question I want to address, whether it can be realized at the level of field theory.
Sorry,
Yes.
just before we launch it, can you go back a couple slides?
Sure.
Thanks. So is the idea that this technology might be useful to explain these enhanced cancellations, for example, at a deeper level than it's been understood so far? Is that the application you have in mind?
That would be an optimistic application, I would say. You know, that it's certainly something to work towards. Later in the talk, you'll see why it's difficult to make clear statements. Basically, it's better if I give some more background and then address that properly. I'd say the broad picture is that yes, we want to understand color kinematics duality to its fullest to try and address this question. Whether what I present today is enough to really say something concrete, well, the answer to that is no. I don't have something concrete to say, otherwise I would put it up front. But maybe this is a route in that direction, and that's one of my concluding remarks. So I'll say more then. Okay, so there are two ideas that I want to leverage in our approach to off-shell color kinematic duality and double copy. The first is that there is a notion of a field theory product of BRST gauge theories and a notion of a double copy of the Lagrangian itself. So these existed in the literature in various guises before. The second thing that I want to leverage is the idea that you can actually make color kinematics duality manifest in the Lagrangian. And again, there have been various approaches to this. And we will build on top of those, on top of some of those. And the final idea is that there is a kinematic algebra associated to color kinematics duality, that the kinematic data of Yang-Mills has a Lie algebra structure to it. So an example of very recent work in this theme is this nice picture of covariant color kinematics duality by Clifford Chung and colleagues. And so this is an incarnation of a Lagrangian realization of color kinematics duality that you can double copy, and it's really nice in the sense that it gives you a closed form analytic expression for the tree level BCJ numerators in Yang-Mills. When I say BCJ numerators, I haven't explained that term. What I mean is kinematic numerators that satisfy the color kinematic duality conditions. We then call them BCJ numerators. Okay, so what I want to do today is not consider a purely classical action. I want to consider the BV action and convince you that it admits a very natural form of what you might call anomalous color kinematics duality that immediately implies the double copy in a very transparent way. So because there are a number of steps involved in this, I think it's helpful just to give you the big picture, which is actually very concise. So the first statement is that I can rearrange the Yang-Mills BRST action into this purely cubic form, where I have the usual color pieces. So the FABCs, the red, are just the Lie algebra structure constants of the color group. The CABCs are just the metrics, so just a delta. And then we've got these corresponding kinematic structure constants, which are really bidifferential operators. And so these are differential operators acting on these fields in some very specified way. And these IJK indices now run over the Lorentz index of the Yang-Mills one-form potential, but also over an infinite tower, a countably infinite tower of auxiliary fields, as well as the BRST Ghost and Nakanishi-Laltrop fields, and also auxiliary fields corresponding to that. So these IJK indices are hiding a lot of content, but really you can put it in this form and it's very natural to do it. And then what the double copy means, it becomes completely apparent. You just replace these Fs with another copy of these Fs, and you replace the color indices with another copy of the kinematic indices, and that's it. That's what we mean by the double copy. At this stage, there's no particular reason to think what we've produced is anything good. And the reason that this is something good is because of the tree-level color kinematics duality that we know is true. And also the fact that it comes along with a double copy of the BRST operator. And it turns out that the assuming tree-level physical color kinematic duality, which is proven, that this BRST operator is a good BRST operator, and it actually implies perturbative quantum equivalence between this double copy action and the BRST action of n=0 supergravity. And the corollary to all of this is that if you just compute the loop amplitudes using the Feynman diagrams of this action, the integrands will obey color kinematics duality.
Sorry, by quantum equivalence, you mean the equivalence of the Lagrangian, which includes the gauge fixing and the ghost, etc.
Everything, yeah.
Not the normalized theory at the quantum level, which is very different, right?
No, I mean the S matrix will be the same. So,
but normalization is very different, and one theory will be finite, for example, for unequal folds. The other will require a normalization, and all the normalization process has nothing.
Yes, so
trivial in the.
That's absolutely right. So these two theories, I suppose the more precise statement would be at the loop level that there is a renormalization scheme such that the S matrix of these two theories is identical, and it's evident what it is. I mean, if you pick a renormalization scheme here, then there is a specific way that it gets transferred over to here, and vice versa. So whatever you do, there is one way of switching between one and the other. So I mean, what I mean is that if given this action, if you were to compute the amplitudes, you would get the same answers given this action, as long as you weren't grossly neglecting the relationship between the regularization and renormalization schemes you picked. I can make that clearer later. So if you take these objects, that you get loop integrands that obey color kinematics duality, but as I mentioned earlier, this is up to counter terms needed for unitarity. But they nonetheless double copy correctly to give amplitudes of n=0 supergravity. Okay, So that was my lightning overview of color kinematics duality. So let's talk about it at the level of Lagrangians. So the first step in this process is to manifest the tree level color kinematics duality of physical gluons. So the physical S matrix at tree level, I want to make its color kinematics duality manifest in the Lagrangian. And there's a very nice trick to doing this. So you just compute with Feynman diagrams. And whenever there is a failure of color kinematics duality, just computing naively with Feynman diagrams, you can find a compensating term that you can add into the Lagrangian that will correct that failure. And then you might worry, well, if I'm just adding terms to the Lagrangian, am I changing the physics? Well, it turns out that you're always just adding zero. There's always a coefficient that sits in front of these terms that you add, that the color coefficients that just sum to zero by the Jacobi identity. But the point is, you take each of these terms in this sum and that vanishes, and you kind of split them up and you divide them between the appropriate diagrams. So I've indicated what goes on for a particular example. You can split this 5-point interaction up amongst the various triples that should satisfy Jacobi identities in a way that you modify the kinematic numerators, but you leave the total amplitude invariant. It's manifest that you've left the amplitude invariant because you've added zero to the Lagrangian. You've added zero in a funny way. But because this is purely tree level, it doesn't get you to loops. This is just, you're stuck with tree level color kinematic duality here. So you can then strictify this, you can introduce auxiliary. So I mean, in this process, I get a Lagrangian that has all point interactions. And this is where my infinite tower of auxiliary fields comes from. I don't want to discuss all point interactions. It's kind of presentationally nicer to turn this into something that's got purely cubic interactions, where I've got an infinite tower of auxiliary fields in the place of those terms. So you can always do this in a way that preserves color kinematics duality. And I get an action that just looks like the things I was showing you earlier, where now these IJK indices don't just run over the Lorentz index of the usual one-form potential, but also over the indices of all the auxiliary fields you needed to make this. And these become, as I mentioned, these F's and C's are differential operators. And they have some nice properties. They on shall satisfy the F's, the blue F's, on shall satisfy color kinematics duality. They satisfy the Jacobi identity. So they're almost like structure constants.
Sorry, I thought you only needed to add this auxiliary field D in your row to have only cubic vertices, but you have an infinite series of auxiliary fields here.
Yes, we've got an infinite series of auxiliary fields here. That's right.
Well, I mean, previously you said this is to add one.
Yes. So then I get cubic diagrams. But those cubic diagrams, it's a neat coincidence that if I do the 4-point amplitude with those cubic diagrams that I showed with just this field, at 4 points you get color kinematic duality representation of the amplitude automatically. But that's just luck. I mean, at 5 points, it would then.
Uniqueness also.
Sorry?
It's also like some kind of uniqueness.
I mean, that term had to be the way it is for gauge invariance. So, you know, that 4-point term had to be there. And then there is an obvious way of, blowing up that 4-point vertex into the 3 ST and U channels. It's basically one way of doing that. And it is the correct way. It's not, it's not unique. You can add other terms and you can change those numerators. But I mean, the obvious thing works. Okay. But if you go to 5 points, this breaks down.
So you get cubic diagrams with the numerators.
Yeah, the numerators work. And this is because you can kind of, you can kind of see why that would happen. You might organize it. It might happen for this triple of diagrams, but this guy is going to belong to some other triple of diagrams. And there's no guarantee that these overlapping sets of relations are all going to cohere and work out at once. But you can make them cohere and work out at once. It just requires auxiliary fields at every point, 5 points, 6 points, all the way up the tower. So here's an example of what gets generated at 5 points. So this is a cubic action. It involves some auxiliary fields, C's, and some other types of C's. It doesn't really matter what all of these are. They're just they just ensure color kinematics duality. But that gives you some idea of what's going on. So let's just summarize. Having done all of that, we get this cubic action that if I compute with the Feynman diagrams, where I understand that I have to sum over topologies for the auxiliary fields, then out pops amplitudes that are automatically in the color kinematic duality respecting form. And what the next step is to generalize this to tree level amplitudes, still only tree level, but where I include the full BRST complex. So I do the non-kosher thing of putting ghosts and anti-ghosts and longitudinal gluons on the external states, and then still demand that I have color kinematics duality. This is not something one would ever normally sensibly think to do. I'm putting unphysical states on the external lines, and then I'm demanding color kinematics duality. But you can see the intuition of why it might be useful, because you can begin to see why you could glue together tree amplitudes to build loop amplitudes, and then have the ghosts and the longitudinal gluons, all the modes running in the loops. So now these IJKs run over the ghosts and anti-ghosts and the Nakanishi-Lathrop field. How do I know I can actually do this claim of extending color kinematics duality to the full BRST complex? If you just relax transversality, so I'm considering longitudinal gluons right now, then tree level color kinematics duality fails. Even if you've made the physical gluon tree level color kinematics duality manifest, relaxing transversality, it then fails again. And it's not difficult to convince oneself that you can always add a term to Lagrangian that will repair this color kinematics duality failures for all of the various Jacobi relations that you need to satisfy simultaneously. So 5 points, there are 9 of them. And you could do this by adding a vertex. But the problem is, unlike the physical color kinematics duality, these vertices are necessarily non-zero. So you have to add non-zeros to the Lagrangian. And you might worry that you're spoiling the semi-classical equivalence of these theories. But the basic principle is the same. You add some, so this is at 4 points. I add some 4-point term, and I can split it up amongst these the ST and U channels, and then enforce color kinematics duality. And the crucial point is that really all of this amounts to a special gauge choice, which makes sense. Really, putting unphysical modes on the external states of the S matrix shouldn't be a gauge invariant statement. That this is all unphysical, gauge dependent. And you can see how to do this. The intuition. I mean, the fact that you use the Lagrangian point of view actually makes this kind of obvious, but the basic intuition is that whenever color kinematics duality fails because of longitudinal gluons, the compensation is always due to a term of this form, because when I make them transverse, it must vanish. So it's always the divergence of the potential times some other stuff. And you can always implement this correction by a shift in the gauge fixing functional. And it's convenient. You don't have to do it, but it's very convenient to shift the Nakanishi-Lathrop field by the same. That just ensures that in terms of the new Nakanishi-Lathrop field, everything just looks like you're in Feynman gauge still, but you've just got these new terms added to the Lagrangian. So the summary is that longitudinal color kinematics duality, that's color kinematics duality that holds for non-transverse gluons, just corresponds to a gauge choice. And then given this, we can use the BRST Ward identities to transfer this color kinematics duality of the longitudinal gluons onto amplitudes with external ghost states. So a typical Ward identity would relate an amplitude with backwards and forwards polarized gluons on the external lines to something that has a ghost and an anti-ghost pair. And you can do this in a way that preserves color kinematics duality. And it's essentially the thing that you had to do by BRST invariance. I shifted the gauge fixing functional. The new ghost terms that I add to the Lagrangian are just the BRST operator acting on this shift in the gauge fixing functional. So it's what you had to do is the right thing to do. So at this stage, we've introduced, okay, so this was all, this is all at some, I've added a 4-point term. I want to do the same trick of strictifying, making everything cubic. And at this point, I've now got a very analogous form of this action, which we call the BRST color kinematic dual action, where now the IJKs run over the BRST complex, as well as a tower of ghost auxiliaries, and also the auxiliaries that we already had there from the previous step in this argument. And just to make it explicit, this is what it looks like at 4 points. So this is the Yang-Mills action corrected up to 4 points that manifests color kinematics duality for the full BRST complex.
So you have to do it order by order, or is that a formula for the whole thing?
No, having a formula for the whole thing would be remarkable. That would be really nice. But no, it proceeds by induction, and so we only know how to compute it inductively. But we can, I can go to the next step. I know exactly what to do. It's just laborious.
You mean you can show there is no obstruction to the arbitrary results?
Yes, yeah. So the proof goes along the line. Well, it's a standard proof by induction. You assume that you have it at n-1 points, and then you can prove that you can boost it up to n points. So there's no obstruction at any order.
But you include new auxiliary field each time.
Each time. So that you've got this infinitely growing tower of auxiliary fields. The reason this is actually useful in any kind of sense is that if you want to compute up to n points, you don't have to have the whole tower. This is all perturbed. We could just chop it off. And then you do all your calculations. If you go to higher points, things will go wrong, and then you have to work again. But up to any given order, it's always a finite number of fields. And ready for our considerations, that's all we're interested in. I would say that's all the double copied program is currently interested in. It would be really nice to have some kind of resummation, but I don't have anything clear to say about that. I think once we understand the mathematical structure behind this a bit better, there's perhaps some hope for that, but at the moment, I don't see it. Okay, so the final step in this this is tree level color kinematics duality for the BRST fields on shell. So momenta squared is 0 everywhere here. And I want to relax this last condition. Now, I can't do this with a shift in the gauge fixing functional. You can always, using the same kinds of arguments, you can always find a term to add to the action that will do the job for you. But it's just a question of how do you generate it. And it's actually not so hard to think how one might generate it. It's roughly the same argument as I made before, where previously I had that these additions must vanish when you go transverse. These additions must vanish when you go on shell. So they're always of the form some polynomial in the fields f times box on one of the fields that you're interested in. This is whatever field you're putting on the external line, we're relaxing the momentum to. And you can always do this with a non-local field redefinition of this form. And having done that, you have off-shell color kinematic duality for the full BRST complex. And then you really can glue these amplitudes together, tree-level amplitudes together, to get loop integrals that obey color kinematics duality. So you've realized loop color kinematics duality for the integrands prior to renormalization or regularization. But there's a price to pay for this operation. When you do a non-local field redefinition, you can't just argue it away with dimensional regularization. It contributes non-trivial Jacobian determinants that don't disappear, and they induce counterterms that are required to ensure unitarity. Basically, we don't want the auxiliary fields propagating. This comes to your question. In this case, if we didn't include these counterterms, those auxiliary fields really would propagate, and we've actually lost generalized unitarity. So if we go on the unitarity cuts of the loop amplitudes, we won't just get the tree amplitudes of the physical spectra, we'll get tree amplitudes that include the auxiliary fields propagating. And these counterterms do exactly the job of just killing those pieces. So in this sense, you get this manifest color kinematic duality. It's manifest in the action. It's manifest on the full Hilbert space of all states, pre-Hilbert space, but is anomalous on the physical Hilbert space in the sense that you have to reintroduce these counterterms that can spoil color kinematics duality, and we don't have a good argument to ensure color kinematics duality for the counterterms themselves. And this is perhaps related to the questions of UV finiteness. If you could understand the color kinematic duality properties of the counterterms, then you'd really be onto something, but we don't have that.
The Young-Mills algebra is anything semi-simple the algebra would do. How about the dimension of space-time? You have mentioned it could be part of the quantum.
Yes, so the dimension of space-time for all of this discussion is irrelevant. I mean, up to the fact that I mean, you could say, well, in D equals 3, I don't have any propagating gravitational degrees of freedom. It's just that you get double copied into pure scalars. So think n equals 8 times n equals 8 in 3 dimensions would give you n equals 16 supergravity. And all the propagating degrees of freedom are in the scalar coset and its supersymmetric completion. So up to that caveat, the space-time dimension, it has not been invoked here at all. This is all dimension agnostic, which is why I didn't highlight it.
Sorry, question. What about IR divergences in 4D? Is there anything interesting to say there?
Probably. I haven't thought about it at all.
Okay. It hasn't been like in light of this BMS algebra and asymptotic symmetries. Is there anything interesting to say there? Where
I'm the wrong person to ask. There are people that I have worked with who have done work on the double copy of BMS and those kind of concepts. I don't want to mischaracterize what they've done. I could try give an answer, but I'd probably get it wrong, and then they tell me off if they ever saw this.
But it's the opposite as for the divergence. The divergence of gravity are very complicated and uncontrollable, whereas Young-Mills are very controllable. And on the other hand, the IR divergence of Young-Mills are very hard to compute and to live for. Whereas the gravity one are kind of simple.
Yes.
So they can be, well, at least
complexity
non-conservation. It's like the other way around.
It's been flipped. Yeah, that's a good question. No, I don't have anything sufficiently clear to say, but I definitely think it's interesting. Okay, so to recapitulate, I'm going to show you this action once again. Sorry, I never changed the notation. It just looks like the same thing over and over again. We've got the BRST part, and I've actually extended it. All of this story goes through for the BV action. It requires extra words and extra work, but there's nothing conceptually different to what I've said. So here I've included the anti-field, and this you can think of as the BRST operator acting on the Yang-Mills field and all the auxiliaries and all the ghosts and everything. So this is just the usual BV action. I've done some manipulations to put it in this form, but there's nothing interesting there. The crucial point is that now the capital F's and C's obey not on shell, but as operator equations, exactly the same identities as the semi-simple Lie algebra structure constants. That is to say that the kinematic F's are structure constants of a kinematic Lie algebra. And actually this structure of there being a kinematic Lie algebra was first noted for the self-dual Yang-Mills theory, where you can make it very explicit. You can really write down what these structure constants are and show that they solve the Jacobi identity by Ricardo Montero and Donald Connell. And this has been followed up in various ways. Here, these F's are more complicated because we're considering the full Yang-Mills theory, not the self-dual sector, but we really have the exact Jacobi identities. And
you have a consistent truncation to the number of points you have been reaching with your set of auxiliary fields, etc., so that you can define the identity of two.
Yes, that's right. That's exactly the way we think of it. So you could, in principle, make these indices go off to infinity, but we would think of it as just being up to some points. This is all true. And then when you go beyond those points, these identities will fail. Okay, so yes, and as I said, this automatically, now if you just compute with Feynman diagrams, this automatically gives you integrands that are loop color kinematic dual. But as I mentioned, because I've neglected the counter terms here, I've not added them in, that unitarity will be will fail, and really adding in these Jacobian counter terms will destroy the color kinematics duality of the loop integrals. And the consequence of this is that the standard proof that the loop double copy really works no longer at least straightforwardly goes through, because that relied on generalized unitarity. So we can't invoke that anymore. But in fact, it doesn't really matter, and you can kind of, I mean, it's nice to have two different ways of approaching the same answer, and this just gives us another way of convincing ourselves that the double copy really holds. Okay, and that brings me to section 2. How am I doing for time?
Yeah, so you have like
15 minutes, okay. So this was the idea of, now that we've put the action in this form, we can double copy it. So let's consider two parent theories, an untilted theory and a tilted theory. And let's just assume that they admit these factorized cubic forms, where actually I can be fairly agnostic about what the two Fs really represent, whether they're gauge group or kinematic or both gauge group. At this stage, I can be agnostic. And I could just do this operation where I take these two theories and I can say, well, I'm going to take the blue from one theory and the red from another theory and produce a third theory. Or I'm going to take both the reds from both theories and produce a third theory. And I can do this in 4 different ways. The two famous ways are the double copy, where I take the reds and I replace them with blues. And then there's the other one is the zeroth copy, where I take the blues and replace them with reds. Really, I should say, in this case, the reds are Lie algebra and the are color, and the blues are kinematic. So those are the two famous examples. But at this stage, the notion of formally taking a singamy of parent theories is completely independent of the prior discussion. It's just something you can do. And then you get these double copy Lagrangians in the kind of obvious way. So you get the double copy, the zero copy, and you can imagine I could have taken the reds from here and put them here. And if these were Yang-Mills theories, all I'd be doing would be changing the Lie algebra. So I just get back Yang-Mills theory with another Lie algebra. It's not very interesting, which is why no one ever discusses it. So the example that I have in mind is Yang-Mills cross Yang-Mills. And in this case, this field with two kinematic indices contains with it in the graviton, the carbon 2 form, the dilaton, all of the ghosts of the standard BV quantization of this system, plus all the auxiliary fields that accompany this. Remember, these things are bearing a tower. These A's are bearing a tower of auxiliary fields. And I can do the other thing where I do go with color, and then I just get boring biojoint scalar theory. So at this stage, I want to conclude that n equals 0 supergravity is the double copy of Yang-Mills, and we can all go home, and I finished 15 minutes early. But it doesn't quite work out so simply. You should be very suspicious. I didn't mention color kinematics duality in this notion of double copying. And so isn't this overly general? Can't I just take any two theories and produce a theory and it's good theory? Well, of course not. So the first observation is that semi-classical equivalents rarely needed tree-level color kinematics duality. So the good old color kinematics duality. And in this Lagrangian double copy, what this is doing in terms of the tree amplitudes, it's really just making this replacement. That's all it corresponds to. And for these amplitudes to be good amplitudes, I needed color kinematics duality. So this only really works for theories that obey color kinematics duality for tree level physical amplitudes. And this implies by construction that if I take this action and I compute any tree level amplitude, it will be a good amplitude of n equals 0 supergravity, all by construction. And this was really an observation that goes back to Zwiebern and colleagues, and they did it explicitly up to 6 points. But what about quantum consistency? And this is where having a BRST operator is important. So to put it another way, I've got this Lagrangian, it's got all of these ghost fields, it's got some gauge fixing. How do we know that it's really a consistent quantization? How do we know it's a consistent gauge fixing? Well, there should be some BRST operator that annihilates the action and squares to zero. And indeed, there is an obvious candidate. It's the one that you get from the double copy itself. And part of the utility of writing it in terms of this BV form is it tells you what you're supposed to do. If the rule in the action is just to replace the red with the blue, you can see here I've got a FABC, and I just want to replace it with the blue. And then I also have the corresponding, because I'm taking these two theories and I'm combining them, I have the corresponding BRST operator of the other theory, where I replace its red with blue, and I get these two objects. I get a Q left and a Q right, and they combine into this Q double copy, where explicitly they're written like this. And you can show that for Yang-Mills theory, explicitly, that these Q left and Q right give you diffeomorphism, at the linear level, give you diffeomorphisms, and the usual two-form gauge transformations, and gauge for gauge transformations, and all that stuff. And then the final step is that because the original BRST operators, the fact that these annihilate the action and square to zero can, and this is true for generic gauge groups, can only depend on the generic feature of the structure constants, i.e. the Jacobi identity. Those identities can't depend on anything more than that. I mean, of course, you could construct BRST operators that do depend on more, but we're being completely generic here. And in the generic case, they can only rely on the Jacobi identity. And because these Fs satisfy precisely the same Jacobi relations as these Fs, these relations just hold equivalently. I mean, it's almost trivial to see. So then we've got an action that are semi-classically equivalent. Their tree amplitudes agree. They in fact agree for all fields, the unphysical ones as well. And there is a well-defined BRST operator, which implies quantum equivalence. And we get to conclude that at least order by order, perturbatively, Einstein is the square of Yang-Mills. And as I mentioned, there's a straightforward supersymmetric completion of this. The interesting part in the supersymmetric completion is that when you double copy a fermion with a fermion, you get a field strength, not a gauge potential. And this is just, I mean, you can see that exactly if you just follow your nose here, but it really meshes with the string theory intuition that in the Ramond sector, you get field, you can articulate everything in terms of field strength without ever talking about the Ramond potentials themselves. Another nice thing that popped out of this was that it generates a generalization of Sen's mechanism. So Sen introduced a way of writing down an action principle that imposes self-duality for self-dual p-forms, field strengths. You can generalize this, you can relax the condition that it's self-dual and just consider an analogous action that describes the physics of arbitrary p-form field strengths. And that's exactly what comes out of this. It's a kind of a neat coincidence. But given that Sen was motivated, his construction was motivated by stringy observations, here we're considering the products of fermions with fermions in the context of super Yang-Mills, there's some coherence to it all. Okay, so in the last couple of minutes, I suppose.
Yeah, 5 minutes.
I can talk about the homotopy double copy. So what are homotopy algebras? I mean, the simplest way to introduce them is that they just generalize usual algebras, matrix, Lie, associative, commutative, whatever algebra you have in mind, to include higher products. So whereas, but these higher products aren't just arbitrary, they have to satisfy higher relations up to homotopies, and these homotopies are themselves encoded in the higher products. So the standard example are Lie algebras, and you can generalize them to L-infinity algebras, and these actually first arose in the context of string field theory. So for a Lie algebra, you've got a grade 0 vector space, you've got a grade 0 bracket on the vector space, and this bracket satisfies anti-symmetry and Jacobi relations. And for an L-infinity algebra, it's relaxation, if you will. You've got arbitrary n-ary bracket. So you've got a unary bracket, binary, ternary, all the way up. These still are great. I mean, this is now a graded vector space. So these are graded antisymmetric, and they obey homotopy Jacobi relations. That is, you write down the standard Jacobi relation and it fails, but it fails up to a homotopy, a chain homotopy. These are chain complexes, and these are chain homotopy, which is just a standard homotopy. And you could do this for anything. So you can do it for associative algebras, you get A-infinity algebras. They are, as far as I know, the earliest example. They're famous due to Jim Stasheff, and they're associahedra, and all of those things are related to them. And then there's commutative algebras. Now, I wanted to tie these L-infinity algebras to BV quantization. And the kind of most conceptually straightforward way of doing that is to flip to the Cheveley-Eilenberg formulation of a Lie algebra. So rather than considering a Lie algebra, I can consider the free tensor algebra over the dual of its grade shift. So this one here just denotes the fact that I'm giving the Lie algebra a non-trivial grade. I'm making it grade -1, and then I dualize so they become grade 1. So you can think of them as ghosts. So these, and then the free tensor product just says, you know, these are just anti-commutative now. And then I can consider the most general Q that I can write down. A Q should be a degree 1 differential operator. So it's got a square to 0. And because it's degree 1 and the only things that I have around, so this should be degree 2, the only things that I have around are these degree 1 T, so it's got to be quadratic in T. Because the T is anti-commute, these are antisymmetric structure constants. And when I square this, I just get out the Jacobi identities from this F. So it's just another way of saying what a Lie algebra is. And then I can just translate that to the L-infinity algebra picture. I do the degree shift, I take the dual, I form the free tensor algebra over it, and I introduce the most generic Q that I can write down, when now I've got arbitrary powers of T, because this was a arbitrary positively graded vector space, so I can have as many of these as I like. Sorry, not positively graded, just arbitrarily graded. And so I can have as many of these as I like, and then Q squared just gives me the homotopy Jacobi relation. So that's a really neat way of summarizing what those relations are. And then you can kind of see the connection to BV quantization. It's this Q corresponds to QBV. And these structure constants just encode the interaction terms in the Lagrangian. You build the Lagrangian using those. So the Yang-Mills story, we'd have this L-infinity algebra, which is a chain complex, just contains the ghosts, the fields, the anti-fields of the fields and the ghosts, and then the trivial pair, the Nakanishi-Lalchuk fields, and the anti-ghosts and their anti-fields. And then there's a homotopy Maurer-Cartan theory that gives you the field strengths and gauge transformations. In the same way there is a Cartan killing form on a Lie algebra, there's what's called a cyclic structure on these L-infinity algebras. And then the BV action is just the inner product using the cyclic structure of some generalized one form with all of the mu i's, which were the higher products in this L-infinity algebra. And that gives you the BV algebra of, that gives you the L-infinity algebra of the BV quantization of Yang-Mills. And then the physical quantum equivalence, it corresponds to, well, actually, semi-classical equivalence corresponds to what are called quasi-isomorphisms of this L-infinity algebra. Those are isomorphisms, those are morphisms of these L-infinity algebras that are isomorphisms on the cohomology. And the intuition here is that the cohomology is where all the physical information is, and you want to preserve the cohomology. And the reason this is slightly more general than just general isomorphisms is these kind of quasi-isomorphisms physically include stuff like field redefinitions or introducing auxiliary fields that can just be integrated out. Any operation you can kind of think to do to a quantum field theory that leaves it invariant is encoded in these quasi-isomorphisms. Okay, so this L-infinity algebra for Yang-Mills factorizes into an A-infinity algebra and a trivial L-infinity algebra, a Lie algebra, and this kinematic piece. And the combination of this kinematic piece and scalar piece gives you a C infinity algebra. As I said, the color is the gauge group. The kinematics, you can just think of as a graded vector space of all the Poincare representations of all the fields that are involved in the construction I was telling you about. So they're the ghosts, the physical gluon field, the Nakanishi-Lautrop anti-ghosting, all the auxiliaries it's just the representations carried by those fields sit here. And then there is a factorization of the cyclic structure into the Cartan killing form of the Lie algebra, this kinematic piece, which can kind of obviously be read off by what these representations are. These are just singlets in the tensor product of this with itself. And the obvious inner product on scalar field fields. Okay, so now that I've done this factorization, the double copy becomes replacing this color with another copy of the kinematics. And in this big table, I've given you the result of all the fields you see, excluding the auxiliaries. You can digest it if you want. It's not particularly illuminating. Yeah, I highlighted a couple pieces. So there are the diffeomorphism ghosts, the graviton, the Calderon 2 form, its ghosts, and so on and so forth. And the action pops out of the double copy. So this is just the kinetic term that comes out. And you can show that there is a canonical field redefinition that would get you from this to something that you'd immediately recognize as Fiat-Pauli plus Cal-Bremond plus dilaton. A field redefinition is almost completely obvious. You can read it off from the double copy of the BRST operator. So you just act with the BRST operator on these fields, and you don't get what you expect on the other side, rather than getting the Nakanishi-Lautrop field from the Q on the anti-ghost, you get some mess, and that mess is what the field redefinition for the Nakanishi-Lautrop field is.
This is just the free.
Yeah, this is just the free theory. So that's right. I showed that the 4-point thing for the Yang-Mills earlier. You would just double copy that to get the next term, but I haven't presented it. So, but there is more to this homotopy algebra story. And I think this is where it gets a little deeper. And this is really due to an observation by Michael Reiterer in work that I think has really been underappreciated. I think perhaps because the presentations are a little inscrutable, it's hard to kind of pick out what's really going on. But he actually gave a proof of on-shell tree level color kinematic duality for the physical gluons by identifying a correspondence between a particular formulation of Yang-Mills theory and these BV box infinity algebras. This was very special because he used this Zapin-Costello complex. It's only valid in 4 dimensions because it involves having the self-dual. It's like a first order formulation where you include the self-dual field strength. So it's really only in 4D. And why any of this worked was a little opaque, but actually it's very natural. And it becomes very natural. There are these rather like he's picked them out of the air from divine inspiration identities that these BV box algebras have to satisfy. But there's a way of thinking about it where they just become completely natural. And that's in the context of what we call Hodge complexes. So if you think of Hodge de Ram theory, this is an analog to it where here you'd have D and D dagger, and then the commutator of D with D dagger gives you the version of the Laplacian. And this is just a generalization of that idea, where it's generalized to modules over twisted Hopf algebras with some central element. So what you should have in mind is the Hopf algebra of constant coefficient differential operators, which includes box. That's the case for Yang-Mills, and you can consider modules over this. And that gives you automatically these Hodge complexes. And then using that, you can define these BV box algebras. And the short story is that the axiomatic structure of the BV box algebra corresponds to perfect color kinematic duality. And if you relapse it to its homotopy algebra, the BV box infinity, so you have this infinite tower of products, that's corresponds to the case where you integrate out all the auxiliary fields. So you have everything just phrased in terms of the Yang-Mills gauge potential, but you have all of these higher point terms. And this infinity relaxation is all of those higher point terms. Okay, I fear I've run out of time. So should I mean, I've got one more slide.
Very
Yeah, I've got one more slide.
very quickly summarize.
So phrasing it in this way actually suggests a number of generalizations. So for instance, there have been work on color kinematics duality in ADS backgrounds. And here, in our context, what becomes the obvious thing to do is to say, I told you that the Hopf algebra of interest for Yang-Mills and Minkowski space was constant coefficient differential operators. I just want to trade it with the universal enveloping algebra of the ADS isometries, and then just turn the handle. I don't have to do anything more at that stage. I can also do Bagalamba Gustafson theory in 3 dimensions. So this has been shown to obey color kinematics duality, and but it's a color kinematics duality that's not mediated by cubic diagrams, but rather quartic diagrams. And this corresponds to having Emery BV box algebras. So I can replace the BV box algebra that's built on a binary product with one that's built on a ternary product, and that gives me the BLT theory. You can introduce matter couplings using what are called many sorted BV box algebras. And then there are some more speculative relations to string theory, which we hope to flesh out, where where the Hodge complex of interest now becomes the usual Q, this should be B naught equals L naught system, where Q is the BOSD operator. I guess the final thing I'll say about all of this as a kind of advertisement is that one of the bonuses of this way of thinking about things is that I never, to enforce color kinematic duality, I never needed to do a loop color kinematic duality calculation. Though that's the really tough part, right? I just do everything at tree level where it's algebraic and I've got full control. I never need to use any ansatz. I just turn the handle and then I get the loops for free, up to the issue that I then have to introduce these counter terms in the renormalization. So that suggests a dramatic increase in computational efficiency, but there is also a price to pay that because we've got this Lagrangian perspective, it's always in terms of Feynman diagrams. So I don't get to use any of the really nice machinery of the on-shell amplitude community. I guess the ultimate goal would be to kind of bring these two together and see if there's some way of, some middle road that does the best. Okay, I'll stop there.
If there's any question here or in Zoom, if someone wants to ask in Zoom, just unmute yourself.
I have a question, it's very basic. So, in GR, the classical story is that pure gravity without matter is one loop finite, but then it's not normalizable. While we have instead for Yang-Mills, we have a proof of renormalizability, at least one orders of computational theory. And so, how does that fit in here? Because if I think of gravity as some square or this double copy of Yang-Mills, how does a theory that is perturbatively renormalizable, the square of Yang-Mills, give me something that is only one loop, or does it also include like some other pieces that converters that make it renormalizable?
No, that's a helpful question. I mean, I suppose I didn't really make how that would work clear, but I mean, the fact that Yang-Mills is renormalizable certainly doesn't imply anything for gravity, even through the double copy. When you double copy, you double the momenta in the numerator. So there's, you know, the power counting changes, and you don't expect automatically to get something renormalizable. And indeed, we know you don't. I mean, that's so. The miracle that you're looking for in the n=8, the maximally supersymmetric case, is some miracle cancellations that happen at the integrand level. Whether or not that actually does happen. So on the one hand, you could say it's certainly possible. We've got instances where that does happen. Something that should diverge by all rationale doesn't diverge. On the other hand, that happened in n=5 supergravity, where I don't think anyone would argue that that's going to be perturbatively finite. So the thing that you're kind of resting your hopes on happens in theories where you don't expect it to work through the whole perturbation theory. But that's not conclusive, right? I mean, it might be that in N=8 there are some extra ingredients, with enough supersymmetry, these things go hand in hand. We just don't know the answer. But yes, the naive picture of gravity being non-renormalizable is not obviated by the double copy.
But also Young-Mills phenomenalizability also follow from the stability of the BV action. So here, is there any reason to believe that the BV action which satisfies color kinematic duality is actually stable, meaning that when you compute the positional deformation, etc. So the BV master equation, you find something that will still preserve color kinematic, which is not in the elasticity debate.
No. So you're asking whether if I do the most general field redefinition that preserves the bracket, the anti-bracket say, that whether color kinematic
And the master equation.
and the master equation, whether color kinematic duality will survive that? No, I wouldn't expect that. It's a very special point.
Okay, so if there are